Partitioning for template functions on persistence diagrams, and again we're going to have, if I can get it correctly this time, Sarah Tymochko?
Tymochko. Yeah, so sorry, I'm back. But this is a project that I primarily worked on, so the last was more my collaborator's project, this was more my project. So this was similar project to what Luis presented on earlier. We didn't know the other was working on this at the time, so we sort of came up with two alternate approaches to similar problems. So I'm going to work on the template function featurizations again. So this method is based on the template function featurization method by Munch and Khasawneh. So again, it's a method of taking a persistence diagram and projecting that into a higher dimensional Euclidean space while preserving some of the topological structure. And then using vectors for machine learning is much easier than trying to deal with persistence diagrams directly. So their method of doing this was based on approximating these continuous functions. So a quick overview again of how this process works. So we're going to choose a collection of these functions that are continuous and compactly supported on the upper half plane. We're going to view persistence diagrams in the birth lifetime coordinates again because it makes everything a lot easier. So looking at continuous and compactly supported functions there. And then for each function, we're going to evaluate that on each point in the diagram. And then we're going to sum that up over all points in the diagram. So given a collection of these functions on a single diagram, we map that diagram to the evaluation on a bunch of these, or by a bunch of these different functions here. So we're going to choose this template system in a way so that they separate diagrams. So what we want is a collection, a finite collection of functions, so that for every pair of persistence diagrams we feed in, at least one of these functions evaluates to something different, because if the diagrams are different, we want our feature vectors to be different, otherwise there wouldn't really be a great advantage to that. So we're going to pick our template functions so that this works nicely. And this method has a lot of nice theoretical guarantees, a lot of which Luis mentioned earlier, but I'm going to skim over for the sake of time. But this method does have, is backed in a lot of theory of approximating continuous functions. So one example of a function that fits this template function format is a tent function. So the tent function sort of look like these little squares, where at the center it's going to evaluate to 1, and then it's going to linearly interpolate down to 0 at some radius delta around that point. So to get our collection of these, we're going to pick subdivisions on our space, our birth lifetime space here. So it's kind of hard to see the lines, but our parameter d is going to be sort of the number of subdivisions we make. So in the picture at the bottom, it's going to be 5. And then we're also going to consider a little epsilon shift away from the diagonal. And by diagonal, I mean the x-axis here, because we've rotated everything. And that's just to help with issues of compact support, because things get wonky when we cross the diagonal. So we're going to just avoid being close to the diagonal entirely. So another example of the functions that fit this is the interpolating polynomial functions. So these are defined in 2 dimensions here, where we're taking the product of these products of fractions. And again, this evaluates to 1 at one point and 0 at the rest of the points, and then it interpolates in between them. These are typically used to approximate continuous functions. And an example plot of these, again, is shown here. So the location of the plot corresponds to the location of that center point. And so, as was mentioned earlier, we're going to use these as templates by sort of shifting around what point we're looking at. So the tent, we're really thinking about moving that physical box around. The interpolating polynomials, it's not as localized, but we're sort of thinking about shifting this center point. So it's going to change the way that this interpolation happens between the grid points. So, an example of how this works with the tent function, because it's a particularly nice little example. We have a very simple diagram here plotted. It's only 5 points, say, in our persistence diagram. As we move, so for that template function, we're going to evaluate it on the 1 point there. We get a value. We're going to shift it over, evaluate, and so on. Then when we hit multiple points, sum it up so we get a bigger value, shifting it over again, then we move up to the next route and continue this. So this is how our system works. Skipping a whole bunch of steps, we get this nice vector for shifting this point around. Again, this works similarly for the polynomials, except it's not as nice to visualize because this intent function is a really nice little localized square. But the polynomials, you can sort of think of the same shifting process. So the motivation for my method, which is an adaptation of this, is sort of looking at an example like this, where we have a whole bunch of persistence diagrams plotted on top of each other. But you can see that placing our grid, we have a lot of wasted space where no points are located. So we want to sort of localize and choose our template system to focus on these areas where the points are concentrated. So the way we're going to do this is we're going to combine all of the persistence diagrams in our training set, forgetting any of the labels, just stacking them on top of each other. Then we apply k-means clustering. So in this case, we have 3 clusters on our diagram, and we don't particularly care about the clusters, but instead what we're going to do is just take the bounding box of these clusters. So that will tell us general regions where there are high densities of points, so where we should be focusing our attention. And so then we're going to apply this sort of same grid system, but applied to the smaller box rather than to the entire space. So on each one of those little boxes, we'll superimpose a grid and then do that same shifting process and concatenate everything at the end. You can see that some of the shapes of the boxes are not so nice, so we have a method of adapting the parameters in the grid so that it fits nicer to the particular shape of the box, but I won't get into the details of that. So the first data set that we tested this on is this manifold experiment as sort of a proof of concept, where we're going to draw a bunch of samples from each of these spaces, compute their persistence diagrams, and then see if we can classify how this works on this example. So these are spaces that we think topology should be able to classify, so it's sort of testing to make sure we aren't messing anything up by using this adaptive system. And so the results of using the tent functions as our template functions are here. The blue line is the method without partitioning from the original paper, and they were using both 0 and 1-dimensional features combined, but ours we separated it and tried a bunch of different combinations. And one interesting thing on the left is that the our method, which is in orange, sometimes goes above the method in blue, getting better accuracies, except we're only using 0-dimensional features, and they're using both 0 and 1-dimensional features. So we're sort of forgetting a bulk of the information and still doing just as well, if not marginally better in some cases. So that's sort of an unexpected result, because we do know that 1-dimensional homology is important in classifying these spaces, so we're not entirely sure why that classification is working so well. And then when we use the interpolating polynomials along the bottom row there, we are getting pretty much improved classification across the board as we increase the number of diagrams we're looking at. So the different colors are just different variants of choosing the features. But either way, we're getting good accuracies, as we would expect, because this is a pretty contrived example for the case we have. So again, this may seem familiar. We're using this Shrek data set, which is meshes of 15 people in 20 different poses, and then we want to predict which person it was, regardless of what pose they are in. And so the persistence diagrams are computed using some sort of parameter that goes into into the heat kernel signature that's computed on the mesh. So we're going to look at over these different parameters how well we do. And we're also going to compare it to the multi-scale kernel, which was sort of the first paper that did this topological method of machine learning on this particular data set. So sort of comparing to how well they did the first time. So here the blue is that multi-scale kernel result, and they set a pretty high standard, getting close to 90 or above accuracy across all of these different parameter values. So our goal wasn't really to beat them, but just to compare how well we did to them, because they did set such a high standard for these topological methods. But the orange line there is the method without partitioning, and you can see that for a bunch of the rest of the colors, which are our methods, we are improving. We may not be doing great, but we are improving upon the original cases a lot of the time, and occasionally getting slightly above the multi-scale kernel for a couple of those parameters. So while we may not be getting 100% accuracy across the board, we are improving upon the original method, which was sort of the goal here. But then when we use the interpolating polynomials, one thing to note is that our method isn't that drastically different than the method without partitioning. The orange line with the other colors is pretty close, so we're getting pretty comparable accuracies here. And we think that this is because the polynomials have support that's globally defined across the entire region. So they're picking up, when you don't use partitioning, they're picking up on some global behavior of the persistence diagram. But then when we isolate them to a smaller region, we may be sort of losing that global interpretation, and now we're just limiting it to a small area that it may not have that same intuition. So with the 10 functions, it seems to improve it drastically, whereas with the polynomials, it doesn't seem to do much because of that global nature of the functions, whereas the 10s are already localized. So in addition to getting pretty good accuracies, we were able to reduce the number of these template functions that we used. So the blue lines there are the number of template functions that were used without partitioning, and the other ones are how many functions we were using. So in some of the cases where we are beating the multi-scale kernel, for example, we're using closer to 150 features, where the without partitioning was using over 400 features. So we do drastically reduce the number of these functions that you need to select, as well as selecting them in a more localized way. So it's a nice method of looking at smaller regions of the diagram rather than the whole thing entirely. So it may be application dependent, but if the local features of the diagram may be helpful, this is a nice way of focusing on those. So yeah, thank you to my collaborators, Lisa Munch and Dr. Firas Khasawneh. The code is online in GitHub. It is not in the master branch yet, but we are working on that. So hopefully that will be updated soon. And my information is listed there. So thank you all for listening to me twice.
All right, we have some time for some questions. Do you want to start?
Thanks very much. When you said, in defining your template functions via the k-mean, the bounding box of k-mean clustering,
Yes.
did you say that you forget about labels and you union all your diagrams or all your data, all your point clouds together?
Yeah, so it's within the training set, forgetting about any of the labels to begin with. We just do it on all of the diagrams together and then reattach the labels.
Have you considered doing something similar to what Cedar does to try to find distinguishing regions where you union all of those diagrams of a particular label, generate templates, do the same for the other labels, then generate templates with the regions where they're not overlapping?
We have not done that, but that definitely would be something to look at. So maybe a sort of in between of my method and Luis's method would be a nice way of looking at things. Thanks.
Any other questions?
Using the k-means clustering, do you see any effect of the granularity of the number of clusters and how that affects your algorithm?
So like how we're selecting the number of clusters? Yeah, so it doesn't seem to change it that drastically. We did test variety, but sticking close to like 3 or 5 clusters seemed to work pretty well across the board. So you don't actually need that many, and it doesn't that drastically reduce or increase the accuracy either way.
We have time for a few more questions if anyone else. Do you remember?
Along very similar lines, was the choice of k-means dictated by just computational efficiency, just really fast, or because of course you could use DBScan or whatever to select a number of clusters automatically,
Right,
instead
yeah.
of having to hand pick 3 or 5 or something.
Yeah.
But obviously they're not slow, so is that the primary reason for choosing k-means?
Yeah, we picked it primarily because it's a more simple algorithm and
Yeah.
it worked nicely. But the way that we have the code written, it is you could change it if you wanted to. So that's
Sure.
definitely something to go forward. The method is very adaptable to picking different clustering methods, picking different of these template functions, and so on. So there's many different features that you can select as a user to modify it.
Anyone else? No more questions? All right, let's thank our speaker.